Hello everyone. Today we're going to start on 1.3, which I talk about two very basic geometrical objects that you have learned in geometry. They are lines and planes. So of course you already know what they are geometrically, and you might even know something about them algebraically also. But we are going to talk a little bit more about from a multivariable aspect. How do you describe lines and planes? So let's start with something that's very simple that you remember first. So in geometry, you have learned that the equation of a line is represented by this equation, y equal to mx plus b. And I like to call this equation the second most popular equation that high school math student would know. And the first one would be a squared plus b squared equal to c squared, Pythagorean theorem. So this is probably the second most popular. And in this equation, you have the x and the y, obviously representing the two variables involved. And then m represent the slope and b represent the y-intercept. Nothing new here, you have already learned it. What I want to talk about is the following. So this is the equation of a line, but only in a certain dimension. So this is the equation of a line on the xy plane only. This only describes a line on the xy plane, or what we refer to as R2. Reason why, because this equation has two variables involved, and those are the only two variables involved. So in this case, you can think of it as y equal to mx plus b involve two variables. And those two variables are x and y, and therefore in R2. The problem is that this equation actually cannot express any line in dimension higher than the xy plane, or in higher dimension than R2. And yes, I know some of you probably thinking like, well, can I just add more variables to it? And yes, you can. As a matter of fact, that's what we're going to be doing. The problem is that by adding more variable to it, it actually doesn't keep it as a line. It actually represents something different, as we eventually will learn more in this chapter 1, as well in chapter 2. So the problem is y equal to mx plus b cannot represent lines in higher dimension, such as R3 or higher. So then what to do is the following. A line in R3 or higher must, and I do mean must, so never try to show me a line in R3 or higher using any other expression other than this one, must be represented by something called parametric representation. So what is a parametric representation? Well, you actually learned about it back in BC Calculus, hopefully toward the end of the year. And I'm hoping that this year, because of the pandemic, you guys still have learned it. Parametric representation basically meaning that in a parametric representation, all the variables are defined by a new set of variables. And this variable has a special name. They're actually not called variables. They're called the parameter. So how is that different? So let's take something that you probably remember learning last year and try to explain. So give you a very simple example. So last year, we call that a circle in R2 on the xy plane can be represented the following two ways. Oops, sorry. Can be represented the following two ways. And that distinguishes the two different way to represent any object in space. One is called equation and the other one is called parametric representation. So what's the difference between the two? So one way to do that is by the use of what we call equation. Another way to use it is by what we call parametric representation. So what's the difference between the two? In the case of a circle, excuse me, in the case of a circle, we can think of the represent a circle using an equation would be this equation. X squared plus y squared is equal to r squared. Well, actually, you know what? Maybe I shouldn't use r. Let's just say we have a circle of radius 1. How's that? X squared plus y squared equal to 1. So in this equation right here, we basically have these two things that they are called variables. And the important part is the following. So this is what's important that you have to understand. In an equation, the two variables are directly relating to each other, meaning in this equation, x squared plus y squared equal to 1. If I change the value of x, it would affect the value of y. If I change the value of y, it would affect the value of x. So x and y are directly relating to each other, and changes made to one would affect the other one. And in this equation, there are only two variables, and we represent this equation to be in R2, which have only two variables involved, and they are x and y. And that's an equation form. And as a matter of fact, for the past, I would say in 5 years, when you first learn about algebra, back in maybe 7th grade, maybe 6th grade, you have been working with equation. So now, what is the difference between parametric representation? So now, hopefully some of you remember what is the parametric representation of a circle. So for a circle, the parametric representation is actually, notice, not defined by one single equation, but instead defined in this case by two equations. X equal to cosine t and y equal to sine t. And in this case, notice that number one is defined by two equations because in parametric representation, each variable has its own equation. Unlike in equation form right here, one equation will relate all the variables together. That's how it works. But in parametric representation, each variable must have their own individual equation. And also, more importantly, is each variable is defined by the parameter or parameters, depending on how many do you have. Okay, so very different, because in this case, in this scenario right here, maybe I shouldn't do that. Okay, in this scenario right here, x and y are the variables, and then t is what we call our parameter. And also very important in parametric representation compared to equation is the following. In equation, the variable directly affect each other. Like in the case of this equation right here, x directly affect y and y directly affect x. As a matter of fact, in this equation, very likely that we eventually define one of them to be the independent variable, the variable that we change. And then the other variable become the dependent variable, which means is the variable that get changed based on how we change the independent variable. While in the parametric form, x and y do not directly affect each other. Okay, there's no direct relationship between x and y based on the information given, or based on the equation given here. But x and y both change according to the parameter t. So by changing t, t would change x and y together. So in a sense, in a parametric representation, the two variables involved, x and y, are technically defined to be dependent variables. And the t, the parameter, are basically act more like the independent variable. Now, of course, then some of you might be thinking, then why don't we just call t the independent variable? Isn't that easier? Why create a new word, parameters, to describe what happened? Because of the following. In the equation, you have the variable x and y, and they are in R2, and therefore we will be graphing the correlation between x and y. And in this case, x squared plus y squared equal to 1, because when you plot all the points x and y together, they form a nice circle. In this scenario right here, the problem is that how many variables do you see in this expression? Well, there are x and y, but there's also a t. Okay, and therefore it's kind of look like we have 3 variables involved. And if there are 3 variables involved, wouldn't this picture is in R3? But no, the problem is we are also refer to this as in R2. Because in this scenario right here, only x and y are considered variable. T, even though it behaves like a variable, we actually don't want to count it as a variable, which is the reason why mathematicians refer to this t not as a variable but as parameter. So important to understand is that in parametric representation, you have variables, you have parameters, but only variables are being graphed onto a graph. Parameters actually does not get graphed onto the graph paper. They are actually working behind the scene, while x and y are what you actually see. So that's the main difference between parametric representation and equation. So when you have something in an equation form and you rewrite it into parametric form, most likely what happens is you have more equation because each variable has to have their own equation, and you also have more variable, but those extra variable are technically called parameters, and they actually do not appear in the graph. All right. So now come the important thing. So now that we have an idea as to equation and parameter, so now of equation and parametric representation, now let's get back to what we want to talk about in the beginning. In the beginning, we talk about lines, and we know an equation form of a line that will allow us to describe a line in R2. So now what I want to do is talk about what if I want to describe a line not in R2 but in R3 or higher. See, the problem here is a line definitely exists in R3, R4, R5 or higher dimension. We know they exist because, first of all, we live in a 3-dimensional world, and if I have a most likely a laser pointer, I can actually shoot out a laser beam which actually takes the form of a line. Okay. All right, some might argue that take in the form of a cylinder, but yeah, that's true. But I'm going to assume that a line is more like an infinitely small cylinder. Okay, and a line does exist in R3. The problem is y equal to mx plus b does not allow us to describe a line in R3 because there's a z coordinate that is changing also. The problem is we cannot add z coordinate into our y equal mx plus b to form a line, because if we do that, we actually form something completely different. And we will talk about what that is later on. So don't worry if you don't know. Remember, I cannot teach you everything that you need to know in one day. So some of these things will have to remain a mystery until we get to them. So, but we cannot just add an extra variable in. So what we need to do to represent a line in higher dimension is to learn to represent them in what we call parametric representation. So let's talk about how to represent a line in a parametric representation. And I do want to clarify is that parametric representation will allow us to represent a line in any dimension, as meaning that it can also represent a line in R2. Okay, it can represent a line in R2, two-dimensional space, meaning like on the piece of paper that you're drawing, or R3, like in the room that you're in, and you can simulate a line by using a laser pointer and see the laser beam. Or in high dimension that we cannot visualize, like fourth dimension, fifth dimension, and on. But the representation is exactly the same. As a matter of fact, parametric representation of a line is more universal. It can be used in any dimension. While y equal mx plus b, the equation of a line, can only be used in R2. Something worth writing down for yourself. So how do I represent a line in parametric representation? Well, we need two things. So what are those two things? Number one, we need a direction of the line. And number two, we need a starting point on the line, a point of reference on the line. And you can think of it as like more like a starting point. And if you think about it physically, parametric representation actually is more natural to describe a line. Imagine the following. Imagine I ask all of you to stand up in your classroom right now. Don't do it because of social distancing. But just imagine the following. If I ask you to stand up, everyone stand up in the classroom right now from where you're sitting. Okay? And where you're standing is what we refer to as a point of reference in your classroom. And we can imagine your classroom is a R2 space, the XY plane. So you're all standing, and the point that you're standing on the floor would represent a point on this XY plane. And now what I'm going to ask you to do is I'm going to ask you to rotate around and look for a direction that you want to go. Okay, and once all of you have a direction they want to go, then you're allowed to only move either forward toward the direction that you're looking, or backward, meaning opposite direction to the direction that you're looking. And if you do that, guess what? You'll be walking a straight line. Your path will represent a straight line. So that's basically what these two things is about. When you stand up from where you're sitting, you are creating a point of reference. And then when you pick a direction that you're allowed to walk, that direction, whether you're moving forward or backward, would create the line that you want to describe. It's not hard. I mean, I would imagine ever since you first learned how to walk, you know how to walk in a straight line. Okay? It's not difficult. So what's difficult? What am I teaching you? I'm not teaching you how to walk in a line, because you already know how to do that in, I don't know, 3 years old or 2 years old, or whenever you learn how to walk. So you already know how to do that. So what's difficult? What's difficult is now what we try to do is try to understand how to mathematically describe this process. That is usually what you're learning in a math class that presents a challenge to you. It's not what you try to describe, but how to describe it using this system called math. So how are we going to describe a line parametrically in math using the system that we have developed? Well, I need to know how to represent the two things I need, the direction and a point of reference for a line. And actually pretty easy. For direction, we have what we call a direction vector that allow us to describe which direction are we going. And some of you might be thinking, well, doesn't a direction vector have a direction and a magnitude? And you are correct. We will talk about what the magnitude would do eventually, but not right now. Once again, remember, I cannot teach you everything in one day. But we need a direction vector, which we're primarily going to use it as a way to define which direction we're going. And a point of reference, since will be a location in space, we will need a position vector. So I believe the textbook used these two things. The textbook used the vector u to be the direction vector and vector v to describe the position vector. So how do we actually form a line? So the way it works is to do the following. So imagine I have this one line right here. And here's where the origin is. And now I want to describe to you what is this line. So how do we actually do it mathematically? So first of all, you have to understand is, for mathematician, we do not describe, well, actually, let me rephrase. For geometry, from geometry standpoint, I can describe the line by saying, wait, this is the line right here. That's the line. I draw it out for you, and now you know where it is. That would be from a geometrical standpoint, if you're studying geometry. But we are studying multivariable calculus. So what I have to do is to describe this line using calculus, using variables. So to describe a line, what I have to do is to think of a line not as an object, a line, but rather think of it as a collection of points. So let's say I have this one point right here. I'm going to call this point vector x. That would be the position of this point on the line. And what I want to do is that this point can be anywhere on this line, so I'll just randomly pick to be here. So if I can describe in a generic way how to get to this point, then I can just move this point to somewhere else, and the description would pretty much stay the same. And some of you probably recall learning something back in geometry. I don't know if you guys still learn about it in geometry. Something called locus. Locus is a set of points that satisfy a given condition. And in here, that is what we try to do. We try to describe a set of points which we will call vector x that satisfy a condition. And when it satisfies all this condition, it will actually line up and form this one line right here in space. So how do we describe this one point? So the way to do that is the following. So remember, we have these two things. And we're going to say, we're going to have vector u, which is the direction. And then we're going to have vector v, which is a point of reference. I wrote it wrong. Give me 1 second. Alright, there you go. Missing the R. Point of reference. So first off, if you think about it, the point of reference must be a point on the line to begin with. So I'm going to go ahead and define this point of reference. It actually doesn't matter where it is, so I'm going to just put it right here. This is my point of reference. Or sometimes referred to as a given point. You must be given a point to begin with so that you know where the line is. And so the vector v, oops, is actually not easy to draw a vector to, let's see. There you go. So here's my vector v that identified this one point on the line. Good. And now what I need to do is show to this one point. So how do I do that? Well, I do know the direction of the line, which is vector u. The only problem is I know vector u would be pointing in the direction to x. Or at most, it would be pointing this way, and then you just do the opposite direction. The problem is it might not have the correct length that will allow me to go from here to here. So meaning that vector u might be this vector. Maybe just this long, but it will be lined up with the line. It just doesn't, it's not long enough to actually get me to here. So now what do I do? Well, we actually learn an operation that allow us to stretch out a vector so that it can be, we can change its length, but not changing its direction. And that's called scalar multiplication. So therefore, if I now want to go from point vector v, from this point, to vector x, what I need to do is travel along the direction of u, but I need to have this vector to be longer. And to make it longer, what I'm going to do is to multiply that by some kind of scalar that will allow me to stretch out my vector. Actually, you know what? Maybe I'll do a different color so that you can see. Let's do green. So now what I'm going to do is I'm going to create this new vector, green one, that is t times vector u. So it's basically the same thing as vector u, but it's longer, so they can actually allow me to go from this point to this point. And that would be how I get to point x on the line. Meaning we do two things. Number one, we would travel from the origin using our position vector to allow us to get onto the line. And then once I'm on the line, I'm going to now look at the direction that I have to go, either vector u or negative vector u, depending on which way point x is compared to the direction u. And then multiply this vector u by some kind of scalar to stretch it out long enough so they can get to the point I want to get to. So that's basically how we describe point x within this line. Now, what happens if point x is not right here, but let's say here, closer to point v? Well, then all I have to do is to basically change the value of t so that I stretch out this green vector to a shorter length. And if point x is further away on the line, they have to change t to be a larger value so that it will stretch out this green vector to be longer. And if point x is on the other side of the line, then what I need to do is to make t negative so they can turn this green vector around onto the other side and have the right length. So therefore, in this picture right here, if you think about it, to get to any point x on this line, all I really have to do is to change the value of t. And that will allow me to actually change this green vector to point to any point on this line, which represented by vector x. And that basically describe what t is doing. T is what we call the perimeter in this case, and allow us to actually move along this line forward and back. And that gives us what we call a parametric representation. So the parametric representation of a line is given by this expression. Vector x is equal to t vector u plus vector v. In this scenario right here, t is our perimeter, which in this picture represent how far to stretch out direction u so they can get to the point x. Vector u is our direction vector. And vector v is our position vector, which is considered to be a point of reference. You can write that down for yourself, or a given point on the line, or sometimes you can think of it as a starting point on the line, which actually I don't really like to think it that way, but it kind of worked that way because it's kind of like this is the point where you kind of start on this line and you can move forward and back from it. And then what is our x, vector x? Our vector x is actually our variable. And here comes the important part. How do I know what dimension this equation or this representation going to represent for a line? Is it R1, R2, R3, R4? Well, in this case, the dimension vector x, vector u, and vector v are all in Rn. So if they are all in R3, then this line this representation represent a line in R3. If they're all in R2, then this parametric representation represent a line in R2. And if all these three vectors x, u, and v all are in R12, then this parametric representation represented in R12. So notice that no matter what dimension you are in, the parametric representation actually stays the same. The only thing that changes the dimension of this parametric representation is what the vectors involve. And x, u, and v, they all have to be in the same dimension for this to work. Okay. I do want to just show you a quick example just to illustrate how this works. So let's do that. And what I'm going to do is I'm going to try to insert a picture. So let's see if I can find a picture to insert. Ah, there you go. I don't know why I cannot move it, but I'm just going to leave it there. All right. Show a very simple example to illustrate. So suppose the following. I'm going to ask you to try to write the parametric representation of a line in the direction of 1, 2. So I'm going to call this my vector u because it's a direction, and contain the point 3, 4. So this would be the given point on the line. We're going to call it vector v. So to write out the equation, pretty simple. The equation would be vector x equal to t times vector u plus vector v. However, I do want to point out, don't get too attached to the vector u and vector v, because those two letters can be used to different things, and sometimes even in the formula they might be used differently. So make sure you pay attention to what does it mean. The parameter t is always multiplied to the direction vector because you are stretching out the direction vector to different length to travel along the line. Position vector always stays stationary because that's a point on the line. You can't change that. Okay, and so in this case our vector x would equal to t times 1, 2 plus 3, 4, or sometimes you see me written this way, t 1, 2 plus 3, 4. And in this case, our vector x is xy, or if you want to write it this way, xy vertically. Okay, so that's parametric representation. Now, show you what the graph look like. So in this case right here, we can think of the graph to look something like this. So the position 3, 4 is right here. So here's 3, here's 4. So that's the point 3, 4. And the direction vector 1, 2, meaning 1 to the right, 2 up. So that would be this direction. So therefore your line basically would just be a line that kind of go in this direction and this direction forever. And that would be the line. And I know it's hard to draw a straight line in this using this touchpad that I have. But hopefully you get the idea. So this is my line, and since the video is already over 33 minutes already, so the last thing I want to talk to you about is the following. This line is parametrically can be represented the following. So one way to represent it is vector x equal to t 1, 2 plus 3, 4. Or xy equal to t times 1, 2 plus 3, 4. What I want you to do is to take a minute to try to figure out how to write it as x equal to y equal to from last year, and also how to write it into a standard y equal mx plus b form. All right. And I'm going to ask you to pause the video so you can try to write that out, and then I'll show you and then once you're done, you can look at the answer. And I'm going to just continue to write out the answer. So if you don't want to know the answer, pause. And after I write down this answer, we'll be done for today. So in parametric form, this will actually come out to be t plus 3 and 2t plus 4. And in y equal mx plus b form is actually equal to 2x minus 2. All right. If you get that, great. If you don't get them, that's okay. Tomorrow during class, ask me, and then we can go over how to do that. All right, and that's it for today. All right, talk to you guys tomorrow. Bye bye.